I want to briefly introduce ONR MIG program, and also the talking about satellite acquisition and flow size distribution retrieval. And then I emphasize on two key things. One is the breakup, how these the thermodynamics play rules in mid-August breakup, and also the why wind tides is so important for sunrise. And then I'm going to have a summary. Okay, MIG program is funded by USA Office of Naval Research. And one is really nice thing is about is the they're using all kinds of autonomous robotics, gliders and buoys and drifters, and also satellite observation. So the reason I'm talking about briefly about buoys because buoys are so important to understand what's going on, what we've seen from the satellite. That's why I'm trying to a little bit briefly go through. And there are so many different buoys, and I want to emphasize on one is a wave buoy. So without wave buoys, without measuring wave, we see something about change of our flow size. We don't know what actually are causing the changes. But having those kind of buoys, and we know exactly what actually not causing the flow size changes. And you will find out what's happening here. So satellite observation, we usually use SAR data, which is a synthetic aperture radar. Obvious reason is because it's very cloudy, so SAR is basically, and most of the SAR data we're using is from TerraSAR-X, from DLR. And then basically we target the, in ONR program, they deploy 1, 2, 3, 4 clusters. And we're following the one with a satellite observation. That's why you see kind of overview of the tracks of buoys. And then these are the SWATs you can see from cluster 1, 2, 3, 4. All different. And then the reason in the title is the winter to summer transition. We want to know, actually want to know the full transition of the ice floes in Lagrangian drift area. So that's the main key observation we're trying to achieve. And that's what we see, all full transition from the winter to summer. Okay? And then we developed the algorithm to actually go from this low SAR data into the, basically what you do is like plot the boundary of all these ice floes, and then you can summarize into the standard Power relationship. Actually, and we drive the alpha value here, the exponential, and then we can see the alpha value can indicate the breakness of the size of the flows, which is a standard the parameter using by the model as well. Okay, I just want to quick go through these the key one of the cluster 1. Cluster 1 is the most south cluster and drift their way, and this is kind of the transition you see. And this red line, I don't know you can see, but these are the location of the buoys. And over the time, some of the buoys lost. So that's why we see some less buoys over the time. And then this is cluster 2. And you can see some of the difference of the between clusters. That's one of the key points I'm also trying to make. And cluster 3 is this one. And then you can see the transition. And you can see the cluster 4 is the most northern part of the buoy. It didn't move much. Actually, it kind of hanging around this area here. Okay, so you can analyze all these data and things, and then you can summarize into the alpha value, exponential alpha, and how it changed from July to August. And then you can also summarize into how the total number of flows the change over time. And I just want to point out two things here. One is we see in mid-August, we can see there are some jump in alpha value, but it's more obvious with the total number of flows per unit kilometers. And these are making questions, why these things happen in this particular moment. And it seems like it's happening across the cluster. So we have a question why. And second question is, if you notice, is cluster 3 and 4 is the more northern part of the cluster, red and green. And you can notice alpha value is a little bit higher than this black and blue, which is in a southern cluster, which means higher alpha value means it's more broken ice conditions in that area. So this is kind of counter institute because we expect the higher alpha in cluster 1 and 2, and this is should be less, but the opposite way. So that's why we have a question why. You can see actually from your eye, actually can see what happened between July 31st to August 12th. You can actually see, you can obviously see something happening here. So you can actually summarize into the flow, the density, which is number one. One means the 100 meters to 200 meters, and 2 is 200 meters, 300 meters. So you can actually see the quick jump of the on mid-August. You can see the increase of flows, and also you can see also in terms of cumulative distribution. You can actually see changes in alpha. Also, you can actually see the slope has been changed significantly for this period. So when we actually we analyze this data, I was so excited because it's a wave, because the wave coming and going to break up. Oh yeah, so I talked to the Martin Doble and Jeremy and who actually deployed the wave buoys, and then so you're going to expect the wave. At the time they haven't analyzed the wave buoys at that moment, so I kind of waiting out. Yeah, you're going to see the big wave coming in on that period. I'm pretty sure. And then what happened is no wave. So it was a really shock. And then so they said a little bit later the wave has a big influence. But before mid-August, actually no wave observed. So we know it's not wave, because without this data, actually we don't know actually what actually causing this breakup. So it's not wave. Then what else? So that. And also, I want to notice is these are the clusters location for that July 31st, and then August and August 20. And you can notice these numbers are the nearest ice edge location from the cluster. So this is a 241 kilometers, for example, and then this one is like that. And actually, you can notice is even this is the nearest one is 73 kilometers, but most of them is about 100 kilometers from the ice edge. So it's not the ice edge phenomena we can see. It's more like interior ice problem, for example. And then we look at the Don Perovich's clear IMB data, and then what this data actually tells. I'm not going to read the details, but from the period from the winter to summer, total ice melt is about 1 meter. Okay, so we got about 1 meter the melt of the ice. Then we had the ice bridge flight on the cluster 2 area, and then if you can see carefully, and you can see this 1 meter thickness draft, and actually there are some, these areas have a thin ice with about meters. So you can expect about this going to be like a kind of melt away and then create some breakup. And then, so you can actually see that the effect in other way as well. And this is the visible data from the USA, called the LIP. Anyhow, they are the 1 meter resolution visible data, optical data. And you can see 2 ice floes with orange and yellow. And then July 30, and then about a week later, and this ice floe was survived, and this one was totally broken. And why it happened? Okay, So that goes to the, we can travel to winter. So SAR actually give you, actually in winter, you can see where is old ice, where is the first ice, and thin ice and smooth ice, things like that. And you can obviously see the difference between orange and yellow flows in summer, which is much less old ice fractions and also smaller, and then larger thin ice, which you can logically think it's going to create more breakup in summer. And another question we had is why the northern cluster have a more higher alpha value, is more broken status of the ice flows. And that question is also go down to winter, because having the buoy, we're tracking the buoy, we can actually exactly see what happened from May to July. And you can see actually these crack, not crack, but used to be crack, and then the refrozen the area, the thinner ice area. And in July, it turns the other, it's the inversion of the SAR images, and you can actually see from here. And then actually it goes here. So it's kind of transition. Actually, what we see from summer is kind of what we kind of expect from the winter ice, which is interesting. And also we can apply similar concept for flow size for summer ice into the old ice, for example. So the idea was look at whether we could see the more old ice, bigger old ice, it can transit to the summer ice like that. And what we see is cluster 2 alpha value is smaller, and cluster 4 was higher, which is already that kind of precondition in winter. Okay, I just want to quickly go through this one. This is Sylvia Cole in press, and this is another interesting, and the ocean ice ocean drag coefficient. Actually, cluster 2, we're expecting less breakup. Actually, consistently low drag coefficient, and also you see the peak of the drag coefficient. This is kind of matching with the rearrangement the ice in deformation, which is we can see from I don't know, you can see the scale and turn into deformation for this period. So I just want to move on to summary. So everyone is talking about thermodynamically driven MIG nowadays, and then that actually the data we show the show actually prove some sort of the thermodynamic driven MIG is going on, and but my question is how was in the past? Because now I'm looking at the very old data, because we always looking at the new data, but sometimes it's good to look at the old data. And when actually this thermodynamically driven MIG actually occur, what point was it? And then to do that, you have to look at the historical data, which is, you can see from Sept, which is the first SAR data we see in 1978. And you can see the broken, and then, but a little bit inside of a area, you cannot see like now today, so you can expect. So we need to more analyze on this kind of data. And also the another important thing I want to cross is the composition of and also dynamics of winter data have to be really carefully studied to investigate how the impact is summer ice. And then having said that, I haven't in the presentation I said the wave is not that affecting the flow size in summer, but it's not actually true. And in some cases, if this one is from Sentinel-1 data, actually you can actually see in a late summer as a huge wave coming in and create this kind of very fragmented ice conditions. This kind of ice conditions will actually consolidate the way and will affect the summer ice in a way. That's the end of the talk. Thanks.
Thanks, Phil. Any questions for Phil? One at the back there.
Hi, I've got a question about why so you showed where you have a number distribution and you've drawn a line straight down where you have a sort of power law on one side. So are you excluding all of the flows on the other side of that line because of the processing or because they're not fit to a power law?
Not fit to.
Sorry?
Not fit to. It,
Not
you
fit
have
to.
Usually they truncate. Yeah.
So you can resolve flows smaller than that in the image processing.
I don't know if Chris is about that. Chris also looking at the yeah. But probably that's a good question. Yeah. Need to look at
And
that.
my other question is, are those p-values from the power law fit? Because it suggests then that maybe it's not very well fit to the power law, even at those larger sizes.
Which one you're talking about?
On that slide there. So is that, if you show this number distribution, and if I understand correctly, you fit the tail of it to a power law. So
Yes,
is the
actually
p-value from your power law fit?
Yeah. Actually, you can actually look at the paper by. So we're using the statistical method. I can show you later about that one. So actually, p-value actually can tell you whether actually it's represent a power law or not, and you can have a look. Yeah.
Okay, another question?
It's more a comment than a question actually, but in some of the distributions that you showed are clearly not power laws, but exponential tails.
Yeah.
And I think if you take that this into account, it would help you also to interpret the data, because when you say that the leads and ridges and other types of structures that there are in the ice are related to the flow size distribution later,
Yes.
and we know that the distributions of some of those structures are log normal, for example, then I think it is very clearly seen in your flow size distributions later. So it's really not very helpful when you just assume that you have this alpha coefficient in all
Yes.
DFs that you analyze.
So that's why we indicate some of them not actually indicate it's not the power law. We indicate in the plot. So
Yeah, okay, but this value of alpha is not meaningful in most cases that you have.
not most cases. I have a
In a lot of cases, okay.
okay.
Okay, maybe one more.
A related question: did you have a look at any of the fits of the power law that that you could actually fit to the smaller end of the distribution, or did you just use power laws? Because obviously there is that tail, so I'm wondering if there are any other potential fits which might better explain that.
Can you say again, please? Sorry. Yeah.
So did you have a look at any of the fits rather than the power law to the distribution?
No, I haven't. Yeah. So because the reason is previously people used that one, and actually Oniska actually suggests I know the paper suggests the other, but we haven't explored that one. But all the data is there, so we can do it. Yeah, but at this moment not. Yeah.
Okay, thanks, Phil.